Welcome to this explainer, where we're going to unpack the monumental 2024 breakthrough of teleporting quantum states over an active public fiber optic connection. If you've ever wondered how the frankly bizarre rules of quantum mechanics are actually going to impact your daily digital life, well, you're in the exact right place. We are finally moving out of the realm of theoretical chalkboards and into the actual physical infrastructure that is going to completely revolutionize how the world handles data. Okay, let's dive right into this incredible statement from Prem Kumar, the computing engineer who actually led this study. Because sending a quantum state through 30 kilometers, that's nearly 18 miles, of fiber optic cable buzzing with everyday internet traffic, that was once considered entirely impossible. Researchers basically assumed that the super delicate nature of quantum information would just be destroyed by the extreme noise of the cable. I mean, think about it. You've got thermal expansion, physical vibrations, and the chaotic scattering of light from thousands of other signals all posing a fatal threat to quantum stability. But against all odds, they actually did it. Now, just to manage our expectations right off the bat, we aren't beaming humans to beat morning traffic, and we're not suddenly downloading movies in 0 seconds. Unlike the sci-fi transporters that ghost human passengers across time and space, quantum teleportation is really about beaming mathematical states of possibilities. It involves taking the complex quantum possibilities of an object in one location, carefully destroying it, and then forcing that exact same balance of possibilities onto a similar object in a completely different location. It's a fundamental transfer of pure information, which, honestly, is arguably just as mind-blowing as the science fiction version. So, here's our roadmap for today. 1. Sci-fi becomes reality. 2. The magic of entanglement. 3. How quantum teleportation works. 4. Overcoming the distance problem. And finally, number 5, building the quantum internet. All right, let's jump right into section 1. Sci-fi becomes reality. So the crazy part here is they didn't just teleport a quantum state in some sterile, perfectly isolated laboratory setting. They successfully hid a delicate quantum photon inside a 400 gigabit per second stream of normal, everyday internet traffic. We're talking massive streams of bank transactions, text messages, high-definition streaming videos, all running simultaneously through the exact same optical fiber. To pull this off, they placed the quantum photons at a highly specific point in the signal, timing it exactly where the scattering of light from all that classical data was minimized. Basically, by threading the needle through that microscopic window of quiet, they pulled off quantum communication without any interference. Moving on to section 2, the magic of entanglement. You've probably heard of this before, but it's absolutely vital to grasp because it makes the whole thing work. When two particles become entangled, their quantum states are no longer independent of one another. Albert Einstein famously called this spooky action at a distance, because the correlation between these entangled particles completely defies our classical intuition about how the universe operates. A change to one particle instantaneously mirrors a change in its partner, and I mean instantaneously, even if those two particles are separated by millions of light years. It's like a direct, unbroken tether across space. So once particles A and B are entangled, their fates are totally sealed together as a single, unified system, totally regardless of the physical distance between them. They essentially form an invisible bridge, and it is this exact bridge, this foundational quantum resource, that provides the absolutely necessary pathway for quantum teleportation to even occur. Without entanglement, the whole shebang just falls apart. Which brings us to section 3, how quantum teleportation works. Let's walk through the exact steps. Okay, imagine a sender, let's call her Alice, and a receiver, Bob. Step 1, they share an entangled pair of particles. Alice has particle A, Bob has particle B. Step 2, Alice wants to send a brand new unknown quantum state, particle C, to Bob. So she performs a joint quantum measurement called a Bell state measurement, which essentially forces the two particles to interact on her particle A and her new particle C. Step 3, Alice then has to send the result of that complex measurement to Bob using standard classical communication, like making a normal phone call or sending an email. Finally, step 4. Bob uses that classical information to apply a specific mathematical operation to his particle B, instantly transforming it into an exact replica of particle C. So the speed of light isn't violated here because Alice literally still has to call Bob to share those initial results. Now, what's really fascinating here is that the original quantum state of particle C is entirely destroyed during Alice's measurement, and it has to be.
This is due to a fundamental law of physics called the quantum no-cloning theorem, which explicitly states you cannot perfectly copy an unknown quantum state. It has to be erased at the source to be perfectly recreated at the destination. So nothing is being duplicated. It's a true, authentic transfer of quantum information from one physical particle to another, definitely not just a simple copy and paste.
All right, Section 4. Overcoming the distance problem. This timeline shows just how rapidly this technology is accelerating. We started with teleporting a photon state over just a few kilometers back in 1997. By 2015, scientists hit 100 kilometers in dedicated specialized fiber optics. In 2017, a team used a satellite to teleport a state 1,200 kilometers from space down to the ground. And now we have this 2024 realization, a shorter distance of 30 kilometers, sure, but crucially performed directly inside an active, incredibly noisy internet stream. This is a real game changer because it proves we don't necessarily have to build a wildly expensive brand new infrastructure from scratch to make quantum communication a reality. So you might be wondering, why was that 2024 breakthrough considered impossible for so long? Why is it so incredibly hard to send a quantum state through a busy public network? Well, to answer that, we have to talk about decoherence. Decoherence is the immediate, fatal threat of a quantum state basically melting into normal reality the very second it interacts with environmental noise. Whether it's a slight thermal change in the cable or a stray wave of radiation, the environment is constantly trying to force that delicate quantum state to collapse. I absolutely love this analogy from the source material. Protecting a delicate photon state against the thermal bumping and grinding of everyday internet traffic is literally like trying to keep fairy floss intact in a raging river. The moment the rushing water touches the spun sugar, it completely dissolves into nothing. In the exact same way, the moment a physical vibration interacts with our entangled photon, its delicate state instantly collapses, and all of our mathematical teleportation data is just lost forever. And when you look at the data, you can clearly see this fairy floss problem in action. As the transmission distance increases, the fidelity, meaning the pure accuracy of the teleported state compared to the original, just sharply plummets. Maintaining high fidelity over long distances is incredibly tough. Overcoming this drop using advanced tech, like quantum repeaters to boost the signal and highly complex error correction codes, is currently the defining challenge of modern quantum physics. If we want a global network, we absolutely have to keep those fidelity levels up.
Let's wrap up with Section 5, Building the Quantum Internet. The endgame applications for society here are virtually limitless. In distributed quantum computing, teleportation allows us to share qubits across vast networks of distant processors. This enables massive supercomputers capable of solving complex algorithms that our current computers simply can't touch. Then there's quantum cryptography, which is huge. We can create mathematically unhackable encryption keys. Because of that decoherence we just talked about, if anyone tries to intercept or eavesdrop on the teleported state, the mere act of observing it destroys it, instantly alerting us to the hack. Linking all these nodes together forms the highly secure backbone of the future quantum internet. As we conclude this explainer, I want to leave you with this provocative thought. Since we now fundamentally know that quantum states can be successfully sent right alongside your daily emails and streaming videos, what will your daily life look like once the classical internet and quantum networks seamlessly coexist on the exact same fiber optic cables? We are standing on the very edge of a totally new era, an era where the strangest, most counterintuitive rules of physics will quietly, invisibly secure and power our everyday digital world. Thanks for learning with us today.